Hello, and welcome to the AI Engineering Podcast, your guide to the fast-moving world of building scalable and maintainable AI systems. Your host is Tobias Macy, and today I'm interviewing Dr. Tara Javidi about building AI systems for proactive monitoring of physical environments for heavy industry. So, Tara, can you start by introducing yourself?
Thank you so much, Tobias. As you mentioned, my name is Tara Javidi. I am a researcher working at the intersection of information theory and generative AI. And as we will get into, I'm here to talk about my role as the CTO of KavAI.
And do you remember how you first got started working in the ML and AI space?
Yeah, so I did my undergrad at Shaif University and then did my PhD at University of Michigan for my grad school in the early 2000s. Now, going back all the way to my childhood, influenced by my own mother, I had always been very interested intellectually and fascinated by the way mathematics and its formalism allows us to do to take a very first principle approach to solving problems. At the same time, engineering seemed very fascinating because it aligned with my values in terms of having a positive impact, socially and physically in the world. But I have to say, unfortunately, I thought I had to make a choice between pursuing a degree in math or doing engineering until quite late in my, it wasn't until second year or third year of my graduate studies that I got formally introduced to the subfield of electrical engineering as part of my PhD studies, and after I had already done a master's in mathematics, and that also overlapped with applied math called information theory, where I ended up doing my PhD work in that space. So I don't know. I know the audience is technical and many people might know, but I don't know if there is interest. I can always talk a little bit about information theory, and if you think that's of interest.
I can add links in the show notes for people who want to dig a little bit deeper on some of the specifics there.
Excellent. Yeah.
Um,
And I think to the audience, this would be interesting because the sort of at least the one bit of historical information that I would share is the word information theory was termed by and was due to a work of Claude Shannon, whose name is nowadays very familiar to folks who are following generative models. And so this field basically focuses on turning information, from conceptual concept, philosophical question of information, and turn it into digital data. And this is really a big part of generative AI models and the way they work these days. So, and that really what transformed my trajectory, not to think of mathematics and engineering in a X or kind of a sense, but more importantly, brought me to this bigger field of information within machine learning and data science. And so that's the sort of background. And now, as a result of this, I do work in machine learning and AI, but from this particular lens, I use this Shannon's way of thinking about data from first principle. And I always ask myself, is there a way of that my training in information theory can really suggest a different way of thinking about digital data, information to digital data, and that others might have missed. So in that sense, that's the interaction that I bring, the sort of the tool set that I bring to the field of AI using this sort of view of information. Philosophically, also, I'm really influenced by Shannon's work in terms of its societal impact, and I'm happy that you will share some of the background, but really, I cannot overstate the impact that information theory has had societally, giving us phones and cell phones and now generative AI. So I'm also very influenced by thinking about societal impact of the projects that I engage in and also having a lot of fun. So Shannon was also very interested in playing games, as again, I'm hoping that your audience are familiar with.
And so, digging now into what you're building at Kava AI, I'm curious if you can describe a bit of what it is that you're trying to achieve and some of the story behind how you decided to spend your time and energy in that space.
Yeah. So I was a faculty at UCSD engaged in the kind of research that I talked about for 2 decades. But KavAI is a startup company that I've co-founded with Sam Bigdelli, my co-founder. And our aim, as you noted at the beginning of the conversation, is to push the boundary of AI to operate natively within the physical world. So at KavAI, from a first principle approach, we are building a new generation of AI systems, and that mimics really the way curiosity functions for humans as we explore the physical world. And that's what I mean by natively processing information in the world. Now, I can geek out on this, and I'm sure as we talk deeper, I will talk about this new generation of AI. But here, that we call curiosity driven AI or artificial curiosity. But here, I will leave the details for that later part so that I make sure that I don't come across that we are only interested in AI for AI's sake. These models are critical to addressing most pressing problems at the intersection of physical intelligence and industrial monitoring. And I can, depending on what you think is interesting, I could talk about both of these aspects, the whys and what of what we're working on.
And yeah, so to that context of industrial monitoring, some of the types of information generation and the actions that you'd want to take based on that information, obviously, there's a lot of work going into things like monitoring, preventive maintenance, et cetera. And I'm wondering if you can just start by giving a bit of an overview of the current state of the art for some of that monitoring and alerting and applications of predictive and prescriptive analytics in that context.
Yeah. So, bigger picture, we are all very concerned about lack of intelligence when it comes to our industrial operations, construction sites, shipping lanes, oil rigs. There's just a urgent need to really up our game and build physical intelligence that recognizes early signs of imminent and often, in fact, very catastrophic accidents and failures. And this is the gist of the problem. Most industrial sites today rely on a mix of human oversight as well as precision robotics in service of precision sensing, and then some IoT systems and platforms that collectively gather information sort of passively sitting in the background, right? So this is sort of the data that comes from the site. Now, each method of collecting data has its own strengths. Robotics, precision robotics, for example, we know of robots that can move sensors very close to the pipes, let's say, and sort of crawl the pipes in search of potential signs of cracks and structural damage, corrosion. And then IoT sensors, sort of have this nice property that they constantly provide you with very green information that sort of they can stream to you. But the current state of the art is that sort of puts these data collection devices in an sort of an arbitrary and rather unintelligent way. They predetermine that, okay, I'm going to put some IoT devices here, and they have some arbitrary schedule of how their robots will scan the site. And as a result, you get this data that has tons of informational blind spots. It misses important information when it's needed because the scanning schedule was not looking at the right pipe at the right time, or the IoT devices were giving too coarse of information or inaccurate information. So what happens is usually the gap is filled at currently by people, or I should say by a team of very experienced site operators that come in and they recognize what information is missing, and then they deploy further inspection by the right tool, to the right source of data for testing for the right or wrong form of hypothesis. This is the current state of the monitoring for these sites.
And given the level of technology and investment that is being made, what are some of the shortcomings in that approach and some of the ways that the lack of complete awareness or gaps in information can lead to things like environmental or economic impact?
Yes. And so I kind of give you the sort of the shortcoming already in my framing of the current answers. So the data, when it's collected in this sort of passive way, it's just or predetermined schedules, has gaps. And humans, even though teams of humans at least are good at hypothesizing about missing data or sources of information or sources of informative sensors, our ability is still rather limited, especially at larger sites with massive scales. So no one operator can walk a 3,000-acre facility every day, especially considering the intellectual and functional costs associated, financial costs associated with walking these sites. Basically, there are just massive fishing expeditions that you take a very experienced, intelligent person to go after, hopefully nothing, right? So day after day going there and testing and seeing, oh yeah, thankfully I came back empty-handed from this expedition is, as I said, both financially not so promising, not a scalable process, but also it creates these jobs that are uninteresting, and humans are not very interested in performing such jobs. So those are, I think, the big challenges of why we are not doing a good job monitoring these sites. And this, I can give you further and further details about how this data is not sufficient for us, and the cost associated with not doing a better job at different sites.
And to the point of a lot of that information collection being very burdensome and a lot of toil, requiring a lot of human capital to be able to actually complete that, I'm curious how you're thinking about the potential for reimagining or retrofitting the actual collection piece of the problem and some of the ways that the design of the solution informs the ways that you're collecting that information. And maybe there is either additional information or maybe there's information that's currently collected that is not actually useful given a more digital approach to it, and just how you're thinking about that overall holistic approach to being able to improve the effectiveness and reduce the level of toil involved.
Yeah, absolutely. So KavAI fills the this gap in information in general, and this is sort of across all physical spaces and all physical sites. As I said, we are building these new generation of AI models we call curiosity-driven AI, and the platform really provides an evergreen bird's eye view of the entire site, and gives this bird's eye view gives then subsequently the ability to the platform to hypothesize physically where and at what granularity the platform should look for the earliest signs of problems and issues. And so basically the platform is enabled in a way to zoom in on more pertinent sources of data and predict problems before they kind of escalate to be catastrophic. Now, at the beginning, we wanted to be very, in a way, philosophically, we have been taking this approach that we don't want to do AI for AI's sake. We want to be very mindful and focused on the real world impact of what we are doing. So in terms of products and services, we have started and so far have been laser sharp focused on the energy production and processing side, where I can give you a bit more sense of how this is done. So our artificial curiosity platform, really what it does is just wants to incorporate the data that you're collecting at these sites. And this is where I can be very specific. For example, you might have humidity sensors. Right now, they're just sitting somewhere. They report it. And if you're in Tennessee, none of it is all particularly alarming. temperature, thermal cameras that the inspectors bring to a site and do every quarter or so inspection are going to show a high temperature, again, if you're in a place that is hot. But if you combine these two with the fluid content of a pipe and put all of that information together, now you can actually build models that are far more intelligent about detection of these early signs. Now, if you put all of that data blindly, then you're like gonna be completely overwhelmed in tsunami of like redundant, useless data. So really, this platform we call artificial curiosity works the same way curiosity helps human beings to operate in the physical world. How do we do that when we are going to an airport and it's very complex? What do? We zoom out things that we believe are not important and focus on things that matter. If we are wrong, I arrive at the gate, it happens to me a lot, and I see, oh, this gate is too empty or there's something doesn't add up, I sort of hypothesize as what sources of information is most faulty in getting me here. This baby was crying, maybe I didn't hear a gate change announcement, right? So that what we call a functional curiosity, the way we actually move our bodies. We go to the an agent that has that source of information. That is what the platform is really allowing us to do, is to turn on and off the sensors and the noise that they bring in.
Now, in terms of the overall ecosystem of AI, large language models have stolen a lot of the attention, but there's still a lot of other work still happening in the context of machine learning, even generative intelligence. And on your website, it mentions that you have developed a foundation model for physical awareness to help power some of that active curiosity. And I'm wondering if you can talk to some of the ways that a foundation model for physical awareness is maybe architecturally similar and maybe more interestingly divergent from a language focused foundation model.
Yeah, so I sort of gave the core idea here, but really the concept here is current models ingest data that is spoon-fed to them, right? The data is already prepared and they sort of take it and turn it into intelligence. When we think about an intelligent human being, we don't only think of them as how they infer or how wise they are when the information is presented to them. We think of people as intelligent when they go out and seek the right information to do something, right? So, and this is this active, this closed loop operation that we built into how the information sources are generated or collected in order to generate data that then will be ingested by the model, is the big differentiator between what we are doing and what the current or maybe the most popular large models, being language or vision models, work, if that makes sense. But I can go in deeper details if you think it's of interest.
Yeah, I think that it's maybe also an interesting corollary is so in a lot of the industrial monitoring use cases, there is a set of machine learning that has become fairly well adopted in terms of supervised learning models where okay, if I have this set of inputs, then this is the type of response. And I know that I need to be able to do some maintenance on this machine because it has hit either this number of hours of operation or it's starting to exhibit some of these symptoms, whether it's a particular noise or change in pitch, etc. But in terms of the generative model context, a lot of that is self-supervised or unsupervised. And I'm curious how you're thinking about the application of some of that more attention-oriented machine learning architecture is applicable to this physical observation style of interaction versus just being a very digital native approach that we're doing with language models, and some of the ways that you're able to do some of that translation of analog signals into discrete digital representations to be able to do that more attention focused learning on that data.
Yeah, absolutely. So you're raising a really important point. So if you think about the way we think about the attention as the architecture in behind much of the success of the Gen AI models, the attention is to the particular tokens that are already being ingested. Now these models have a bottleneck that they cannot handle a very large number of tokens. In fact, long context is sort of the frontier of how good a model is how much token it can actually consume and still produce sensible outputs. So now think about building these systems with data that you're feeding from a completely useless source, not, I shouldn't say useless, but redundant source that is repeating that same temperature reading that it has been repeating for the past month. So in this setting, it's very clear that you don't want to create these, what I say, instead of long, it's a volumetric context, right? If you just tokenize it in a brain-less manner. So that's where this closed loop operation comes in, as how would you actually turn and say, this sensor right now, the readings, I am confident I'm giving an output that is consistent with the reading. So in that sense, it's self-supervised. So I can start reading it less, right? So that closed loop feedback is exactly the differentiator in what we are doing. But the architecture, the architecture components are similar. So you can sort of think about, and now I'm going into way too much details, so hold me, but really you can think of this as a physical attention that goes wider than your narrow architecture by kind of going in the world. And we think of this as the spine, as well as the sort of our limbs and arms and hands going and grabbing the data that you want to bring it into your model.
And the other interesting aspect of that problem is, as you mentioned, you are developing these additional means of data acquisition to remove the requirement of toilsome human activity in that process. And I'm wondering how you're thinking about when you're removing a human from the loop in some capacity, there's still a need to make sure that the digital system and the other information gathering systems are themselves monitored in some capacity. And I'm curious how you're thinking about that aspect of how to ensure that that digital collection has high reliability and resiliency and is able to be adaptable, particularly in the context of a constantly changing physical footprint where maybe you have a factory that is expanding or going through renovations, or there are upgrades of equipment, and just some of the ways to be able to adapt to that constant change.
Yeah, so you're absolutely correct. But we're a little bit lucky in this, luckier than having to solve the problem from the scratch. When you go to these sites, they already have some sophisticated autonomous data collection process. Many of them have ground robots. Many sites have looked into operating drones and so on. So we don't get in the weeds of like building a full, hardware platform for them that is doing all of this. They already have this, and their number one problem is they don't know which one of these devices are useful at any given time. And that is the problem that our foundation model with its spine, which is an OS, really is solving, is really giving them the wisdom to operate these sites. Now, the great news is that these components are becoming more and more advanced. We are getting better and better precision robots. We're getting better and better drones that are very stable. They have their own safety constraints. So that's where we're not getting into the competition of building a full autonomous system with all of these devices. We're building on the power of many of these existing technologies. We're just really solving the main problem, which is now that we have the ability to collect such sophisticated data, which one of these data sources are holding the gold for me as predicting my next failure? And then we really exploit what is there in these sites. And they have done a good amount of investment in technologies along the lines that you have in mind. So we often work with their technologies.
As far as the system that you're building beyond just the data collection and some of the model specifics, I'm curious if you can talk to the overall system architecture of the platform and how it integrates into the workflows and existing systems of the companies that you're looking to support.
Yeah. So the architecture is again very much inspired by the way we call a human intelligent. So the basically the architecture is aware of the devices and their physical sensing modalities. And we in our models we basically the trained model is taking advantage of certain physical laws of sensing. So, for example, when you go away, almost uniformly, does not matter what sensor you're talking about. When you go away physically, you distance yourself from the sensor, the information gets less accurate. So, this is the component that the physical intelligence on the sensing side that we are taking advantage. And then there is an operating system, as I was telling you, that acts like a spine that knows where the information is, but decides what to filter upward towards the model that then uses the tokens to recognize something has changed. There is a major reordering of the factory, and hence the model needs to be re-updated in the spatial configuration sense, and so on and so forth. So this is the architecture. The architecture is really profiling the sensors, creating a sort of an ecosystem of data, and sort of having an integration OS that timestamps and geostamps these sensed information, such that if they become useful, we have these physical laws of where it was collected. Hence, it's correlated to the information in that geographical location, and then the foundation model that is uses this to build hypotheses as where to allocate most of its attention. Now it becomes a physical attention. This is the basic architecture.
And one of the interesting challenges that always comes up when you're trying to introduce either new or different machine learning and AI capabilities into a particular operating context is the user experience around that, as well as the potential for the human operator to have some sort of either reticence or mistrust of the system. And I'm wondering how you think about the ways that you introduce the KavAI platform into these organizations and integrate it into the responsibilities of the person who has to either support or take action based on the outputs of your system, and some of the trust building exercise that goes into maybe giving some insight into why a particular response is created or why a particular recommendation is made.
Yeah, so this touches upon so many different aspects of both technical, but also, one of the things is at the beginning, I said taking this view of like engineering and sort of impact on the world. From the get-go, we were very committed to work with real people and solving real problems. I felt like if I wanted to do AI for AI's sake, ivory tower is not such a bad place, right? So we were very lucky that that decision, which was more like our own value system to work with operators in the energy sector, gave us this possibility to think about what is their problem and what kind of interfaces they use as people who do this job day in and out, and what kind of help we can give them. And so that's why I completely agree with you. The way this data is presented is by far the biggest hurdle for the operators to make sense of it. It's siloed. You need 5 different interfaces to be building, like look at your IoT digital device, and this is handled by your IT team. And then there's an inspector who comes in and gives the data on a piece of paper. So you nailed it. And without going, or giving away too much of our secret sauce, that has been very much in our DNA, working with operators and really making sure that our OS provides the data in a way that is well understood by the operators. Again, and also because we are closing the feedback loop and we need to hypothesize about the sources of pertinent information, that gives us a bit of an advantage in the sense that now that has to be something that the operator is comfortable with, and that needs to be in a way trustworthy for them to really follow our suggestion that, hey, this is where you need to send the next inspection crew.
And then another interesting aspect of building any type of platform or product like KavAI, where we're introducing machine learning across a suite of different contexts and organizations, is that there's the potential for being able to do some level of transfer of information gathering and insight creation from one operating context to another one. Obviously, there are issues around regulation, privacy, et cetera, where you can't directly use data from one organization in another. But I'm curious how you're thinking about the ability for the overall platform to be able to improve and learn from collected information and collected experience to then be able to improve the functionality for all of the consumers.
Yeah, no, you're absolutely right, and this is something that becomes more of an art than science at the level that you are envisioning it. For us, so far, really the name of the game has been understanding the physical world, and when I say understanding, it's from this lens of information, so that we can really ask ourselves, where should the eyes of our cameras, literally, and our sensors, figuratively, are looking at the world. And we would like to understand how to arrange these eyes and sensors, these cameras and sensors across the space. So really the knowledge that we are learning and our model is being trained on is this knowledge of how the information is filling a physical space and what is the physical laws of sensing that is going to be embedded in that process. In that sense, we have not gotten too deep into the site specific sensitive data than that, like these older models would train on your data and your pipes and the arrangement of your pipes to then learn secondary and ternary effects. And that's really interesting as how to cut that pie. But for us, right now, the real knowledge that is transferred across sites is this knowledge of how sensing gets affected by distance, how sensing gets affected by temporal distance, and so on.
That's another interesting aspect, is the question of time in the context of physical systems, where it can have different levels of significance depending on the pace at which the different operations are happening. Where if you're worrying about preventive maintenance for a machine to make sure that you do some repairs on it before it breaks down, you're going to have a much longer time horizon than if you're doing some sort of sensing for risk of explosion, for instance. And I'm wondering how you think about the overall decay of information utility across those different temporal boundaries of the data that you're collecting, and how you think about how to apply that right temporality and the maybe dampening of the signal across those different use cases.
Yeah. So you are raising an issue that often it's true for space as well, but somehow it's harder to convey it. But in time, we all have this really good understanding of a lack of an absolute fidelity, right? Time can tick at the microsecond level, at millisecond level, at day level, year level, and when you take physical world, there is no absolute temporal clock that you would be wanting to, collect the data. If you do it too fast, you get such correlated data that then it will overwhelm you in form of redundancy if you do it too slowly. So that's sort of the gist of what we are doing. And then these hypotheses are sort of the larger memories in some sense that are built into the system to keep track of these longer contexts.
And as you have been developing this platform, working with some of your earlier customers and helping them understand the capabilities and applications of it, what are some of the most interesting or innovative or unexpected ways that you've seen the platform applied?
Yeah. So no, we are still very a bit too early, so I can't tell you reveal too much. But I will say that this idea of hypothesis driven, prediction, this has been really fun. Like we talked about it. We were looking at it from our end, but the first time that we did one of the paid pilot projects, and I could see, yeah, that it works and how well it works and how useful the customer was saying, this will be very useful for me to think about scheduling my next inspection. That was like one of the proudest moments of my career in general. Now we will be making more announcements about the specific projects and so on LinkedIn that I would very much think if your audience want to follow more specifically, they can follow.
And as you have been working in the space, developing the technology, evaluating its effectiveness, what are some of the most interesting or unexpected or challenging lessons that you've learned personally in the process?
Yeah, so the most interesting is something that we haven't talked. I mean, as you said, this is a technical, technical audience. But I think I have to say, in general, the most interesting part has been around growing a strong and exceptional team. These are like really the most interesting lessons that when I look back at the experience at KavAI, that I've been fascinated by, is like how to recruit the best people, how to retain them, how to grow them both individually, but at the same time help them build a collective together. So this was been really the most interesting, how we have been able to cultivate a culture where all of my team members, I can think of them as important individual members with their own needs and their own constraints, but then the team as a whole, vouching for each other and building a collective sense. So that's been the most interesting. Now, you said also unexpected, right? So if I have to talk about unexpected, I would say the most unexpected fact is how much of my time I am on Zoom. Or I should maybe say it, the remote work culture that was created during the pandemic has helped us in ways that I really didn't think about it would be possible pre-pandemic or pre this remote work culture. So we have been able to recruit the best talents from all around the world, and that's really been the most unexpected if I have to pick. And as I said, personally, how much time I'm still spending on Zoom.
And as you continue to build and evolve and iterate on the overall problem space of AI for physical environments with an industrial focus, what are some of the particular projects or problem areas or new capabilities that you're excited to explore?
Yeah, so from a societal perspective, I'm very concerned that we have grown our footprint, technology footprints, in ways that goes way beyond our ability to monitor it. And in one particular sector, and that's energy sector, we have seen the catastrophic cost of doing this from an environmental perspective. And that's where I am really laser focused on. And I really would like to see that these environmentally destructive incidents to become a thing of the past. There are certain ways humans accepted the world, earlier on, like hundreds of years ago, that we think of them as things of the past. And I would very much like this to become a thing of the past, that our children and grandchildren get used to saying, oh, this happened in year 2018, but this is ridiculous. How could these people let that happen? That's what I'm really, really excited, but also very committed to achieve.
Are there any other aspects of the overall application of AI to physical environments, the work that you're doing on CavAI specifically, or the potential for this technology driven improvement to industrial processes that we didn't discuss yet that you'd like to cover before we close out the show?
I think this curiosity driven, this thinking of data generation in an integrated way with generative AI, or I would call it information-centric AI, is really, excites me, but is also a really important topic that I think more and more will create more opportunities beyond what we are working on immediately now. And I will leave it as that.
All right. Well, for anybody who does want to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest gaps in the tooling, technology, or human training that's available for AI systems today.
I think the existing, AI systems are very good at the learning and ingesting digital data, large amounts of it whenever possible. The race for the next generation of AI, however, especially in the physical AI domain, will be really the forefront, or the winner of that race will be architectures that really build on this information-centric AI, this curiosity-driven AI will be the first generation of.
All right. Well, thank you very much for taking the time today to join me and share the work that you're doing at KavAI and some of the interesting challenges of being able to move AI beyond just the digital realm. So I appreciate all of the time and energy that you and your team are putting into that, and I hope you enjoy the rest of your day.
Thank you so much, Tobias. I really enjoyed our conversation.
Thank you for listening, and don't forget to check out our other shows, the Data Engineering Podcast, which covers the latest in modern data management, and Podcast.init, which covers the Python language, its community, and the innovative ways it is being used. You can visit the site at themachinelearningpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at themachinelearningpodcast.com with your story. To help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.